to start by telling you this is a talk about contextual bandits. So I'm afraid I won't have to offer much on the control side of things. Sorry. Okay, but at least I think I hope to show you there's some interesting learning questions here. And I know several people in the audience have worked on related topics. So let's dive in. So this is joint work with my PhD student, Jack, also from the University of Amsterdam, also with Julia, who is somewhere in the room over there, and with Chen Yu Wei from University of Virginia. And Chen Yu made such big contributions on this project that sometimes it felt like he was two co-authors. So I felt it was fair to show you. In any case, so there's another keyword in the title, which is that we're going to work via reduction, which will be a reduction from contextual bandits to linear bandits. And in a way, maybe that's the most interesting aspect, I think, of the talk. So this is on. So it stopped working. Okay, there we go. So for a general outline, there's first the setting. I'll build up from adversarial bandits to contextual bandits to like a more abstract formulation of contextual bandits. Then I'll go over the bounds that we get, the rates that we get. And then the main part is about this reduction to linear bandits and like what the general idea is. Yeah, we'll get to that. So starting off with the setting of just adversarial bandits, which probably be familiar to many of you, is that we're going to operate in rounds. Every start of the round, the learner chooses an arm from a finite set of k arms, and then a loss value for that arm is revealed. And the object of interest is the regret with respect to an arbitrary arm A, which is the expected cumulative loss of the learner minus the cumulative loss of that arm. And the expectation here is over the randomness of the learner. So the learner is allowed to randomize. We're thinking throughout the whole talk, I'm thinking of oblivious adversaries, bounded losses. So that's the introduction. So then to upgrade this to the contextual setting, what we want to introduce is some contexts that determine the losses of the arms. So then things work as follows. At the start of every round, we're going to receive a context, which is a vector in actually in p dimensions. Then we pick an arm and we observe a loss. And instead of competing with a fixed arm, we're now going to be interested in measuring regret with respect to an arbitrary policy. So policy will be a strategy for mapping a context to an arm. And it's allowed to randomize. So when I talk about the loss of a policy, that's actually like the expected loss when the policy, under the draw of an arm according to that policy. Right, so we're upgrading to context now. If you make everything adversarial, like the context vectors and the structure of the losses, then there's nothing to be done here. You can't, it's too difficult. So you need to make some assumptions to make this feasible. And in particular, there are two types of assumptions. And one is the setting of Noy and Olkowskaya, sorry, where it's assumed that the contexts are stochastic. They come from a fixed probability distribution. And then the losses for each arm, they are linear functions of the context, where the coefficients in this linear function are changing over time, and they're actually adversarial. So we don't observe these coefficients directly. We just observe the losses, but they are adversarial. That's the important point. And because I'm assuming this oblivious adversary, I'm assuming that these vectors, they don't depend on anything that's happening in the game. We can think of them as being fixed beforehand. They might depend on the learner strategy, but they will not depend on any randomness that happens during this game. And in the literature, people have considered an alternative setting, which is maybe bigger even, is instead of having random contexts and adversarial loss functions, people have also looked at having a fixed loss function that doesn't change over time, maybe stochastic feedback, and then having adversarial contexts. So you can play around with these assumptions, but yeah, focusing on this specific setting where the contexts are IID and the losses are linear, but adversarial. All right, so this is the contextual bandit problem that I find, like the formulation that I find the easiest to understand. But I'm actually going to generalize from this to a slightly more abstract contextual bandit setting. So that's the next step. And the idea is that if we have all these loss vectors, so the loss vector for the first arm, which is a vector in R to the P, loss vector for the second arm, third arm, we can put them all in one big P times K vector, stick them all together, and then identify the choice of an arm with an action that's also a big vector. And in this big vector, I'm going to put the context in a certain position such that xt meets the arm, the coefficients when I multiply these two together, such that xt meets the coefficients for that corresponding arm. Right? So if I multiply these two together, most of the zeros will meet, most of the coefficients will meet zeros, and only one of these vectors for one of the arms will meet the xt. And so when I take the inner product, I get that the inner product between xt and the coefficients for arm A will actually be equal to the inner product of A and this big theta t vector. So I'm going to reparameterize things in a way where now the actions are no longer fixed numbers, not just the names of the arms. The actions are choices in a random set. It's random because it depends on the context vector xt. And this set still has k actions in it. Right? So in the end, I'm going to receive every round a random set, and it's these type of actions. First one places xt in the top position, then we shift it down by p places, and then next action shifts it down again, we shift down all the way. Right, so k actions, a random set that we're going to get. Excuse me. And then if we're going to go this route, we can also handle more general cases. So let's say we're going to get any random sets with at most k actions in it, and that will be our setup. Right, so we can cover this setup, but also more general things. And then the framework becomes as follows. So every round, instead of a random context, we get a random set of allowed actions that we're allowed to choose from. The learner has to pick an action in this set. It's also allowed to randomize if it likes. We're going to observe a loss, which is the inner product between this big vector theta t and the action chosen. And we measure regret with respect to a policy, where now a policy also observes this action set as input. That was the context before, and then a policy maps an action set to an element of either specific action or maybe an action in the convex hull of that. Right? So randomizing over this action set in expectation is equivalent to playing inside the convex hull because everything is linear. So now policy is going to map an action set to the convex hull of the set of actions. So I think, like, if this is the first time you're seeing this, it's a lot to take in. So feel free to interrupt, ask any questions.
Forget about contextual XT.
Yeah, for most of the talk. Yeah, sometimes I want to refer to like the basic initial setting, but yeah, this is the general setting, and so there's less structure a priori to assume. Right, this could be complicated. Important thing is that the action sets it's still assumed that they come from their IID from a fixed distribution. So that corresponds to like having IID context initially. Yes. So at most k elements. All right. So then in this setting, generalizing from the previous case, it's actually easy to derive that the optimal policy so the one that we want to compete with in the end, optimal policy and expectation, is going to be of a linear form. Because if we want to find a policy that minimizes this expectation, that's the cumulative, expected cumulative loss, where this expectation now also is over the randomness in the AT, then just moving this, because the AT are IID, I can just move this sum inside and get a sum over the theta t vectors. And then we see that the policy, because it's allowed, like this expectation is over AT, so the policy is able to see all the randomness that's happening here, and so it just needs to do the best response to this vector given the action set that it gets. And that means that the optimal policy is the form, like pick the action that minimizes this loss for some vector phi, which is the sum of the theta t's over time. So we don't know this policy because we don't know the sum of vectors theta t in advance, but we do know the form of this policy. So in the end, competing with the best policy means to do that, it's sufficient to compete with the best linear policy of this form. So it's doing this argmin. It's not randomizing, even though it was allowed to. So that's what we need to compete with. All right. So that's the setup. This abstract setup. Here, I should mention that now I'm assuming the action set is living in d dimensions, and before in the previous setting, I had a context living in dimension p and k possible actions. So then, to translate, d is, in this example, d is p times k. Right? So that's why I use p and not d initially to distinguish. Okay, so that.
For the sum of the thetas.
Yes.
Seems a bit counterintuitive.
Regardless of the distribution of
like,
yes.
So if we would tell the policy that it's time t,
Mm-hmm.
it still is.
Well, it has to be fixed over time, right? The policy. So it can only do something for that's the same behavior over all times. Yeah. Yeah. Should maybe be pi of a, like for any. Here. Oh, yeah, that should be a. Should be a, yeah, there's no, yeah, sure. You have to use that, it's IID. Thanks. Yeah, I think it's surprising. You also see that like the stochastic setup is important to for this. All right, so so then let's get to the rates that are known and that we can achieve. So there's a bunch of ingredients. So one is that there's the dimension of the action set. Then there's, I'm assuming that the number of actions in each set is upper bounded by k still. So like a finite number of arms, say. There's a new number, which is how many constraints, how many linear constraints I need to describe the convex hull of every action set. And that will come into the computation time for the algorithm that we develop. And then there's another concept that is important in this context. So some works assume that you can get additional samples from the distribution of the action set, or pre-context samples that you can then use to estimate some aspects that you might like. Like for example, with context, you could try to estimate the covariance distribution. So these are free samples outside of playing this game, sort of offline samples. And if you assume that you have access to those, it's like what people call it's like having access to a simulator. And of course, it matters if you have this access or not. It's easier if you do. And so the rates and the computational complexity that people get also depend on whether they have access. So related works, the regrets in general should grow like square root of t, square root of number of rounds. And then the differences are in like how you depend on the other problem parameters. And there are all kinds of trade-offs between dependence on D, runtime that you get, and whether you have access to a simulator. So what I'm showing here is rates up to logarithmic factors in D and T. I'm still showing dependence on K, because actually I'm also interested in the case where the number of actions is very large compared to the dimension. So maybe exponentially large in the dimension. And in that case, like log, say 2 to the D, would still contribute some significant Ds, right? So anyway, so the point is, if we have a simulator, then we can get, say, D square root of T or square root dt log K. If we don't have a simulator, we can also get the D square root of T, but with a very large runtime, exponentially large, some of the problem-dependent parameters. And if we want to go faster, we get the D squared, there's the D squared square root T in the literature. So what are our contributions? Well, one is that, oh yes, and I mentioned like I'm interested in the case where, say, K is exponentially large in D, so it's say 2 to the D. And then, so I'm thinking of this rate as basically being the same as this, right? So this will be like, if this is 2 to the D, I'm going to get a square root of D out of this, which will add up with that, and it will be D squared square root of T. So this is basically the same as that for me. But the difference then is in the computation time, because if K is exponentially large in D, then having polynomial computation time in K is still bad in terms of D, right? And so what we do is we bring that down to, instead of K, to have C number of constraints. And in some applications, like shortest path, there's a huge gap between these two. Like even though the number of possible actions is maybe 2 to the D, the number of constraints you need to describe that is only linear in D. So in some of these kind of combinatorial settings, C can be much, much smaller than K. Right? So the contribution is that if we have such a combinatorial setting, we get a faster algorithm. And then depending on whether we have access to a simulator, if not, we get like the D squared type rate. And if we do, we get the D squared of T. So that's the improvement, yes?
But AT change over time, so you assume that all the AT that will be described by
Yes, so like, yeah, any AT that I get, I can describe by at most C constraints, is the assumption. All right, anything more? Yeah. So then there's this, and then actually it turns out that the approach we use to get this rate, it also extends to the case where we have, instead of T, the number of rounds, if you assume that the losses are between 0 and 1 instead of -1 plus 1, you can also have, instead of T, the expected loss of the optimal policy, which is at most T, but it could be, for some cases, it could be significantly smaller. So you can improve to what is called a first order bound. And for first order bounds, some things are known, but this is focused mostly on this initial setting that I described, like before I went to the more abstract contextual bandits. So then the setup is like the contexts live in some dimension P, at most K actions, or actually exactly K actions. We have the loss of the optimal policy. And then the rates that people get, like if you don't want to have this optimal policy in there, you can get the K and P inside the square root up to log factors. If you do want to get this optimal policy in there, what you would normally expect is that you would just get this rate and replace the T by L star. But no one has been able to do that yet. So instead, what we have in the literature is K outside with an inefficient algorithm that doesn't need the simulator, or K outside with a polynomial time algorithm that does need the simulator. But the second algorithm, even though it's much more efficient, it needs to make a strong assumption about the distribution of the context. So they need to follow a log concave distribution, like a Gaussian or something, maybe truncated Gaussian. What we have here is we have the same computation time as this previous method, a worse rate. Now the P is also outside because my D was K times P. The P is also outside the square root. We need access to the simulator, but we don't have this additional assumption. So it's again a different trade-off. Yeah. So that's the improvement we can also get. All right. So that's in terms of like consequences of the approach. But what I think is most interesting is the main idea of the approach, which is this type of reduction, going from contextual bandits to linear bandits, which to me seems really surprising that this is possible. So what's the idea? Well, if you look at the expected loss for any policy in any given round T, you can take the expectation inside the inner product and give that a name. So that's like you take the action set and you take the mean of that. So that's some operation you can do. And we'll give that a name. Let's call that psi of the policy, because it's no longer random. It's like you take the expectation of the action set over action sets of the action that the policy is taken. So it's like for every action set, the policy takes an action. You take the expectation over that. So you get a point in R to the D for every policy. And then you see that the expected loss here is the inner product between this mean action and the loss vector. And so you can ask, like, which type of expected losses are achievable? Well, you just take the image of all the policies under this map psi, give that a name, omega. And then the types of expected loss that are achievable is like elements of omega times theta t. And then the idea for the reduction, which won't directly work in the current form, but it gives an impression, is to say, well, suppose that we have first a linear bandit algorithm that will tell us how to choose yt in omega. And then we take that output, we find some policy which has as mean action yt, and that's what we're going to play. Then in expectation, our loss will be equal to yt times theta t. So we'll have the same expected loss as this linear bandit algorithm. And we're going to give as feedback to this linear bandit algorithm an unbiased estimate of its mean loss, right? So we just get a sample of at and pi t valued at at times theta t. Like in expectation, that will have this, well, it will have loss yt times theta t. But we give an unbiased estimate of the loss to this algorithm. So basically, we need a linear bandit algorithm that can deal with unbiased estimates of the losses. And we can run that and translate the output back to something that we can play in our original game. And then the regret bound should also translate. Right? So this is like in this form, this is a very, it's still very simple, and this would work. It's important to mention that this reduction has been proposed earlier has been proposed by Hanna et al. In a different setting, in the context of stochastic bandits. So this is not a new reduction, but what is new is to apply it in this context, and we need different techniques to make it work here. But yeah, it's really due to this earlier work. Okay, so it would be great if things would work like this. But there's one obstacle, which is that this psi mapping, it depends on the distribution of the action set. It depends on the distribution D, calligraphic D, and also this domain for the linear bandit algorithm will depend on that distribution. And even if I assume that I have this simulator, I can get samples from D, I don't assume that I have full knowledge of the context distribution or the action set distribution. So this mapping psi and also this set omega, they're actually not available directly to me. So that's why I cannot implement this strategy directly. And what I want to do in the rest of the talk is go through two iterations where basically we're going to approximate this set omega by an omega hat or psi by psi hat based on samples, say from a simulator. So we approximate this by something I do have access to, and then that will cause problems, and then I need to fix those, and then we're there. All right, so basically problems because then there's a gap between psi and psi hat. Okay, so so this is the setup now. We have some linear bandit algorithm. Yeah, this is just the reduction from the previous slide. And if I go and my plan is to replace this psi mapping by a psi hat, which I estimate based on a separate sample of action sets. So independent of the whole game that I'm playing in, I assume I have n samples of action sets, and I replace the expected, the mean action, I replace it by its empirical mean. And then we also get an empirical analog of this domain of all achievable mean actions, right? So instead of omega, we'll have an omega hat. Right, and then if I propagate, instead of playing the linear bandit, will now play over this this estimated domain, omega hat, and we'll map its output to a policy not using psi, but using psi hat. So these are things that we have access to. And this will immediately produce a problem, because now when we report our feedback to our loss to the linear bandit algorithm, this loss is what we observe. Its expectation is still in terms of psi. It's not in terms of psi hat. This is not under our control. So we're going to report biased losses now to the learning algorithm, to this linear bandit algorithm, right? So, but on the other hand, you might expect that if n is large enough, maybe the bias will be small. And the good thing is, like, if we can control this, like n, if we know n, we can estimate how big this bias would be. So we do have some control on the bias, but we need to deal with it. And in particular, we're going to need a linear bandit algorithm that can deal with stochastic feedback, and that's also slightly biased. Yes, question?
Regarding rational aspect too, need to search over all policy, the one.
No, but I'll yeah, hope if I have time, I'll come to that. But yeah, this is also something we need to resolve. Yeah, so this is like the second iteration. It's still not what we need in the end. But I just want to build up like more like research style. Like you have an idea, you iterate until all the bugs are out. Anyway, so this iteration 2. And then we need such a linear bandit algorithm that satisfies these properties. And of course, there are many related ideas in the literature, but not exactly what we need. So we had a side result that says, well, we can build that. And basically, the assumption is, suppose that we have some feedback, which I'll call F for now, which is at most epsilon biased. So it has mean that is not quite yt times theta t, but it's close in terms of some epsilon. And this happens every round. Then the algorithm should promise me that my regret, the linear bandit algorithm should promise me that my regret is at most d times square root of t times something that is maybe linear in t, but it meets this epsilon square root of d. And then there's a parameter alpha here that depends how good this algorithm is. Depends on how good this algorithm is. And is known that the best alpha you can get is 1. But we didn't manage to get that with an efficient algorithm, polynomial time algorithm. So instead of alpha is 1, what we're going to have is alpha is square root of d. And the algorithm that we develop is some version of continuous exponential weights over omega hat, similar to work of Ito, where they also prove a first order bound. So because we're building on that, we can actually also have a bound in terms of L star instead of this rate. Right. So I'm going to focus for the rest of the talk on the rates in terms of t, not the first order L star bounds, just to illustrate the idea. Okay, so this is like an assumption, like, can we have an algorithm like this, and then we show we can have it for alpha square root of d and still be efficient, and then that gives us an algorithm that can deal with this type of biased stochastic inputs. All right, so and the question is, like, is this enough? And it's not, because we need to still account for the fact that there was a difference between psi hat and psi. And if we could make sure that the difference for every policy that we play and also for the optimal policy was always bounded by epsilon, then things would go through, because we could look at, the bias that we have in every round, which goes into this linear bandit algorithm. I could just bound that by epsilon then if we have this guarantee. And also there's the issue that this linear bandit will give a regret bound with respect to omega hat, but that will be close to a regret bound with respect to omega if I have control on the difference between psi and psi hat. Right, so I can rewrite, if I have an upper bound on the regret in terms of omega hat, I can rewrite it in terms of this psi hat for the policies that we play and for the optimal policy, and that should be close then to the actual regret in terms of psi, up to some 2 epsilon for every round. Right, so if I have this type of control, then we're all good. So then the question is, can we have that for all policies that we play? And the answer actually is no, in the sense that if you want to have this type of bound this difference uniformly over all possible policies, like right now I haven't restricted what my policies look like, the policies that I play, so I need to bound it over all possible policies simultaneously, and that's actually false. Like, you cannot, this is a type of uniform convergence result over all possible policies, and it's not going to be small with high probability, this difference. But what we can have is this gap being small uniformly over all linear policies. And we already knew that our optimal policy was linear, so maybe that's good enough. Right, so here's the definitions again, and then the statement is that, this is a linear policy pi phi, and uniformly over all linear policies I can have the difference being small, where small depends on the number of samples I have to construct my estimate psi hat. Right, and this is assuming that this n is under my control. I can make this be as small as I like. So taking n large enough, I can make this smaller than epsilon. Yeah, and so the proof for this is basically a standard uniform convergence analysis, because the losses that we're looking at here, this is like an expected loss, and this is like a uniform average. It's sort of an unusual loss function, but you can, because it's bounded, you can analyze it via some Rademacher argument. Anyway, so we can have this, and then for every specific round, and then we take a union bound over all t, which is cheap. And so this is fine for the comparator policy pi star, the optimal policy, but not for the policies that my algorithm plays, because they might be anything at this point. So then that's a thing we need to fix again. We need to make sure that the algorithm is also going to play only linear policies, and then we're good. Right? And we also need to do it in a computationally efficient way to satisfy Emily. Right? And yeah, we can't fix this by just having uniform convergence over all possible policies. All right, so then what's the idea? Well, it turns out, so I'm now just going to sketch a bit high level. What's the idea? Well, like we have this omega hat, and it turns out that that's a polytope that lives in R to the D. This is not trivial, but it's true. So it's a polytope, but the number of vertices, we haven't bounded that. It's actually a big open question I have, like, can we actually upper bound this number of vertices? But that's not resolved. So it's a polytope, and it turns out that if we have a vertex, so it's like a cartoon of this polytope, if we have a vertex of this polytope, it turns out it's not so difficult to show that there exists a linear policy that under psi hat maps to that vertex. Right? So if I have a vertex, there is a corresponding linear policy that maps to that. So if I can somehow restrict myself to only play vertices, I can find linear policies, hopefully, that that correspond to that. So then I could achieve this goal of only playing linear policies. And the way to do it is to say, whenever we get an output from the linear bandit algorithm inside this omega hat, we're going to decompose it in terms as a convex combination of a small set of vertices. And the number of vertices you need is at most the dimension +1, at least if you don't worry about computation. So at least there exists a small number of vertices such that I can decompose the play as a mean of that. And then instead of playing YT, we're just going to sample from this small set of vertices according to the mixture weights to make sure that in expectation we still have the same loss as before. But now we're only playing vertices, and then for every vertex, I'm going to convert it to a linear policy and actually play that in my algorithm. So that's the final approach. Now we've fixed all issues. There's only the issue of computation. Like, can we do all of this efficiently? And it turns out that what you need in order to do these operations, like find this decomposition and also find the corresponding linear policy, it turns out there's some standard linear programming results that allow you to do that if you have a separation oracle for this omega hat. So a separation oracle is, if you give it any point, it says either the point is inside omega hat, or it will return a separating hyperplane that separates the point from the domain. Right? So if you can do that efficiently, you can solve these problems. And it turns out we're able to construct such a separation oracle. Funny story. So I don't know if you've had the experience of trying to chat with ChatGPT about a research question. So my experience is that it will start brainstorming like crazy and then give you a wrong proof. And then you point that out, it gives you another wrong proof. And so you never get to the point where it actually solves anything for you, but maybe it sort of loosens the mood. Now, Chenyu was actually talking to ChatGPT about the separation oracle. It suggested a proof, and that was actually correct. So surprisingly, it was useful. Like, well, I was really, really amazed. So that's where the separation oracle comes from. It was, I think it was probably a sort of standard thing in linear optimization that we wanted to do here, like this type of structure. So probably in many books, there were related things. But yeah, I'm not an expert in linear optimization, so I didn't know these books. So it was really useful. Anyway, so I should get to the point where I start wrapping up. Yeah, so we have this, what's the final approach? We have this linear bandit algorithm that gets this type of rate. And then, wait, sorry. If we have this linear bandit algorithm, we can get this type of rate by bounding the effects of the bias. And yeah, you see here that there's a first term that's like d square root of t. So that's great. And there's a second term that depends on how many samples I have access to construct my psi hat. So this n. If I have a simulator, I can just take n large enough for this term to be like not dominant. And then we get this rate. So that's the first variant. If we don't have a simulator, the trick that you can do is you can run this algorithm in epochs of exponentially increasing lengths, and you use the observations from the previous epochs as estimates for the next epoch. So estimate psi hat from the previous epochs to use in the psi hat in the next epoch. And if you do that, then you don't control n directly. Like it comes from the construction, and so as a consequence, you get a worse rate where there's like a d square root t. Hold on. Yeah, like this, and then alpha was d to the half, so that's why you get d to the 1.5 in the end here, and also this log factor. All right, so that's it. So the idea is we have this. We're able to handle combinatorial problems computationally more efficiently. The idea is this reduction, for which we needed a linear bandit algorithm that can handle the misspecification. The many open questions. So for example, here the feedback model is this bandit feedback, but in like a semi-bandit feedback model, there's work that says, well, we can deal with a weaker oracle. Like instead of counting the number of constraints of the action sets, if you just have a linear optimization oracle for each action set, that's enough. This under the stronger feedback model, maybe it would be enough in this model as well, but we don't know. Other question is whether we can improve the regret further even if we don't have access to a simulator. And finally, like in terms of first order bounds, I would like to get to know that P and K can both be moved under the square roots. Even with an inefficient algorithm, this isn't known yet. So sort of a pet peeve of mine to figure this out. Yeah, so that's it. Thanks very much.
Thanks, Tim, for the talk. So any question?
Yeah.
So I will still bother you with the computations.
Yes.
So just from the high level, you do a reduction from a contextual linear bandit, so with changing set of actions, but that are relatively simple, to a linear one with the same set of action, but that is more complicated because it is really big. Imagine. So do you have really? I don't know a lot about the adversarial linear bandit algorithm, but at least the stochastic one, when you have a complex set of context, you at some point need to solve an argmin or an argmax of some UCB over this set of context, and this can be hard if your omega set of context is complex, even if it doesn't change. So I wonder if you also thought about, I don't know, is it better to try to not do the reduction in terms of computations, not in terms of regret? What would you propose? Is there?
Yeah, that's a good point. I don't know. I mean, there's yeah. So
when your AT are varying, but I don't know, somewhat easy, like this XT that you place in a different space, for example, it maybe look easy.
Yeah, I don't have a good answer. I mean, there's one funny thing is that also in the pursuit of this first order bounds, there's I mentioned this prior work where with Julia we got we got this rate having access to a simulator, assuming that the distribution of context was log concave. And now the funny thing is that we, in order to get that, we so it's also on that paper. In order to get that, we needed to treat this contextual bandits set, like you're competing with points on the corner of the simplex for the bandit setting. But you can also say, like, let's treat the simplex as a convex domain and do a continuous exponential weights algorithm over this convex domain. And that seems like both in terms of the rate and in terms of computation, much harder. But in order to make that result go through, we also had to go in that direction. So somehow there appears to be a thing that going to these convex domains makes maybe the analysis easier. Maybe it's just more difficult to figure out how to do it otherwise. It's not like for this rate, it's not necessary. They don't go to this continuous set. So sometimes it's not necessary. It's basically, yeah, I don't have a good answer. I think sometimes it makes things easier. It's the best I can say.
Thank you.
So I had one about the square root of d for alpha, basically. So what's the hardness in there? Because you said order of 1 is achievable, but there's some computational issue.
Yeah, that's a good question. This I actually don't know why.
Yeah, because then already with this present analysis, you have d squared at least.
Wait, what with this one? If you could get this, yeah, it would shave off like a square root d factor in the final bounds. Yeah.
So
not
remember what was the hardness or any computation?
Yeah, so one thing we want here is that we want to base the runtime on the number of constraints that describe this action instead of the number of actions in there. And so that somehow forces us to go a different route. But it's not obvious that like maybe this can be improved like with an efficient algorithm. It's the only thing we do is like construct things that like sufficient things, but it's not clear that it should be necessary.